who was able to get to this point, run the first block of code, and get it done. So you're done, you're done.
Everything turned on. Oh, they did like last week at the MIT hackathon.
So you see, it prints all those requirements already satisfied, blah, blah, blah.
Okay. Just curious. Well, I was just there, like programming and everything. But,
Then we get to the second block of code.
Meta that.
Okay, you need to run it as well. This one now imports all the functionalities, all those libraries that we need. Again, once you run it, it will have an asterisk, and once it's done, it turns into a number. So the numbers are actually the executions of the block, so you can keep track. So the first block we ran got the number 1. Now we ran another block. It was the second one to be executed, so you have the number 2.
I'll give it to you.
This is just the setup. This is just to get all the commands and everything that we need in order to make it work.
Does this have to be done every time we log in, or is it a one-time thing?
The installs, once you install it, you already have it on your locally. If we do it on IBM Lab, you will see that it says requirement already satisfied because they have everything installed. We just included these lines of code because if you move to a different computer, we don't want you to figure out what's went wrong. You just run this block. If you have it installed, it will just skip it. If not, it will install.
Yeah, the things you do have to do every time is the import.
Okay.
Because that enables other commands later on.
The import part, this is where you get, specifically you're telling him, from Qiskit, which is the IBM development kit. From it, we want to be able to create quantum circuits, we want to assemble, we want the backend calculation, all this kind of stuff, state vectors, plot spheres, everything we talked about. So this will import everything, and now you have it within your kernel. So your kernel is running with all the information that you need. Right. Now we have some kind of like review again of what we discussed in class. So if you want to read it again and see all the things that we mentioned, like how you multiply all those matrices, how you do a tensor product, which we didn't talk about, but this is like the mathematical description of entanglement. This is how you write it down. So if you want to look at all this stuff, the qubit and Bloch spheres, right? The superposition we said. So our psi has some at state 0 and some of it at state 1. You can read it, but we covered all of it at class. So after you go through all these texts, right, we get to the first time that we actually create a state. So the way we go about it, we define a variable, we call it state, so it's easy for us to track it down. And we tell it to create a quantum circuit with 1 qubit. Just initialize it. If we run this part of code, okay, we have a system with 1 qubit in it because we told it to create a quantum circuit with 1 qubit, and we're telling it plot it on a Bloch sphere. Now, if you remember, we talked about the Vincenzo criteria, so you were able to reset your system and start from the ground state. The way to go about it is you say, when the arrow points to 0, this is the ground state. This is where we will always begin. So if we create 1 or 100, once we just initialize the state, there will always be in the 0 state. All of them will start this way. So this is the starting point. Did you get to this part and it ran and you got the Bloch sphere with the arrow pointing toward the 0?
Yes.
Amazing. So now you basically created your first quantum circuit. You have, yeah, very exciting. Think about it. It runs on a quantum computer, and out of all the qubits that you have there, the system assigned one qubit for you and initialize it to the 0 state, right? We have one qubit for ourselves. Now, we talked about some one qubit gates, right? The beginning, the simpler ones are just a single qubit. We operate on a single one. So here again, you have some more text, and the reason we included here is because we mentioned at class that using the Dirac notation and all this kind of stuff, it's a way to kind of save you the trouble of doing all the matrix multiplication and all this kind of stuff. But if you want to just to look at it and see how it works, you see that if you take the X operator, which is this matrix, and you operate on the 0 state, if you do the multiplication, this is the result you get, which is the 1 state. So this is what the computer is calculating behind the scene. It multiplies all those matrices and everything and makes it easier for us to look at, to visualize it. This is the Hadamard gate that we mentioned. It changes bases, so if we put H on 0, we get plus. On the x-axis, if you remember, if we put it on 1, we'll get the minus. So it moves us from pointing toward 1, from 0 to point to plus, and from 1, it points to minus, right? So it rotates everything 90 degrees. Now, this is where you start to play with this thing, and we want you to try and operate on those qubits to get into a certain result that we want you to achieve. So before that, we'll show you an example, and here you have the syntax. What are the commands and the instructions that you need to use in order to tell the computer to operate on the qubit, right? So these are the examples. You have them here, but I'll show you one of them. So you remember, we always start pointing towards 0. And I want you to point toward 1, right? So we want to do a bit flip. We want to get from 0 to 1. How do we do it? So the way we build this file is that we have all the commands ready. You don't need to worry about the layers and everything that is going beyond it. And we have some space here for you where it says your code here. This is, in this part, this is where you need to put whatever you think the solution is to solve the problem. Okay? So how it works, we define a function, call it lab exercise 1. We define a quantum circuit, right? We want the computer to have this quantum circuit, and we tell it it's just a single qubit. So this is to initialize the system. And if we just run as is, what you'll see is that my system was initialized at the 0 state. We said this is the starting point for everything. Now I want to turn 0 to 1. Who remembers from class we discussed what operator I need to use to turn 0 to 1 and 1 to 0? Exactly.
What? The X?
The X, correct. The X gate operates as a bit flip, turns 0 to 1 and 1 to 0. Okay, so how do we actually do it? We have the syntax here, right? So let's use it. What I'm actually telling it is, on my quantum circuit, which we chose to call QC, this is kind of like the convention. I put a dot because I want to use something on this quantum circuit, so this is how you implement the instructions. What I want to do an X gate, okay? And X gate on what? I want to do X gate on qubit 0, right? So I'll tell it, operate on qubit 0. Now when I run it, flip to 1. Okay? So again, where it says your code here, you want to operate on or in your quantum circuit, you choose which gate you want to use, and you need to tell it on which qubit you want to operate, because technically you can have many qubits in your quantum circuit. So that was the first example. Now, let's try to do the second one. Okay, the second one, we want to get to point to plus x. We want the arrow to come out toward you. Below that, you have again another quantum circuit which we initialize, and I'll give you a couple of minutes to think about it, how you move from 0, 1 to plus minus. It's a change of bases, right? We also included hints. So you want to change from Z bases to X bases.
So like qc.z. Do you write qc.z? Switch the base or no?
We have a Z gate, but Z gate just rotates around Z axis, right? So if my Z axis is pointing up, down, and I'll do it, it basically what it does, it rotates me like this.
Because it starts at 0.
Oh,
Right? What you want to do is do something that moves you from here to here.
oh.
You can go up again, right? And here you have all the more common gates that we will use. If you scroll slightly above it, you will see in the examples we included, if you use the Hadamard gate, you turn 0 to plus, and you turn 1 to minus, right? So if we want to move from the 0, 1 bases to the plus minus bases, we need to use a Hadamard gate. Okay? So how we are going to do it? Again, on our quantum circuit, we want to do something, so I'll put a dot. I want to use an H gate, Hadamard gate, and I want it to operate on the 0 qubit. Now, if I run this part, you will see that, again, we start at the 0 state, we end up at the plus, pointing toward the X direction. Are we okay with this part?
What was the initial state of that qubit?
The initial state is always
X.
0.
Okay.
Always.
It's Z to X, right? What about Z to Y? And how do you do that?
Again, what's going on?
Now you're changing from Z to X to basis. What about Z to say Y or X to Y? Are you still using the H gate or something else?
One way you can do it is, and this goes to like how you think about building algorithms. You can find a matrix, an operator, that will take you directly straight from Z to Y.
Yeah.
You can do it. Another way you can do it is use smaller building blocks that you already have. So I'll move from Z to X, and then I'll do a rotation like this.
Oh, along the.
Should I try to target the most efficient path to do that, or that one that changed
Oh, no,
from
it's around the X.
one axis to
So
the
I
other
think it
one?
stays on the X axis.
It's a very complicated question that you ask, because you would think that just moving from Z to Y in one step it's very efficient, right? But maybe behind the scene, when you need to send the laser pulse we talked about to make it move and shift, maybe it's very hard to do it. So it's better to do 2 easy steps than 1 hard step. So maybe it's easier just to move to X and then rotate.
What are those steps that are classified as easy for the laser that will change the?
It depends on the hardware, on what it is, and actually the computers will let you know what are the native gates that are available on that computer. So it says
the architecture.
Yes, it tells you it has this computer can do this rotation or that rotation. So program your things either in that way, or if you don't, the transpiler will turn it into those.
So the algorithm that I'm building perhaps will be efficient for this machine with that laser,
Yes.
but with that
Very inefficient
laser,
for another machine. That's why it takes a lot of knowledge to build efficient quantum circuits.
Tomorrow we'll show it on classics on the platform itself. You will see that we'll have a code. We'll take something like the last example, which will be like a big one, and we'll run it again, and we'll choose to use IonQ trapped ions, for example, and you will see that you will get 1 circuit out of it because it's really optimized for their connectivities, their gate, the things that they can do. But if then you'll try to run it on Microsoft's computer, you'll see that it doesn't really work as well. But if you tell it, no, start again, take the same algorithm, but optimize it for Microsoft-specific CPU, QPU, you'll see that you get a different design because they are better at rotating at like 90 degrees, and they are better at rotating at like 30 degrees around this axis. And
we're in a state of art on these hardwares. Do we have something like multi-laser that help us to maximize how many moves or spin are more efficient, rather than just have one direction and the other machine in another direction?
that's a
Which one of the technologies like the
It goes
most?
from here, like it goes from here to here.
Okay, so it's more like flexible in this manner.
Question. Actually, I don't know which of the modalities would be most flexible. That's a good question, though.
Yeah.
Are we building? But are we building as a humanity a standard for like this hardware production? To start building algorithm that can be used for different.
We'll talk about it tomorrow as well, and we have like just benchmarking and saying this one is better than this one. But this is a fight of itself. Like people don't agree on what you want to use as metrics and say this is good and this is less.
So perhaps we'll have like in television different type of standards.
Maybe, yeah. Certainly, I don't think we can have too many, because at some point the OEM manufacturers need to build a couple of the modalities and not every single one.
Yeah.
Like a Blu-ray versus, high definition discs. They both.
Why do we look at the rotations that we're performing and not giving the coordinates integer or something? Because when we look at the qubit web right now, there are 6 different positions the arrow can point to. I mean, in today's complexity, at least, that we're able to control. Why don't we just number them like from 0 to 5 and then go to 5, go to 6? Now that's
What you're saying is part of the development that is happening now. It's exactly the point. It's like if you think about classical computers, it's telling the computer, take this variable, put it in register 1, then take another one, put in register 2, then combine and add them up and put in register 3. So this is what you need to do now.
yeah, but what
The idea
is
that
very
is-
simple. I mean, if you have 6 different positions and you want to get to other 5 different positions, you can just memorize the steps you need to take. So it's not like building a whole software model or something. It's like I don't know, 20 functions,
But there's
like 2 lines.
I see what you're saying, but it's much more fine than that. There's not just 6 positions. There's an infinite number of positions because you can point to anywhere you want, right?
Can we with today's hardware? That's the question.
So you cannot point in an infinite accuracy and resolution, right? You have a limit to the resolution. But now think about like if you can move 10 degrees at a time, right? Yes. So it gives you some resolution. But then if you improve your controls and your readout and everything, and then now you can move in 5 degrees every time, now you can do much more with your data.
It'd be the same reason why, you know, we call it XYZ as opposed to 0, 1, 2. It gives a basis of understanding of where you are positionally, and we kind of all agree that this is how we're going to talk about it. As long as we're all talking the same language, everybody understands.
And what's the granularity we're able to control today? Like, how many different positions can we get to today? Because this is like a hardware question, right?
Yeah, that's absolutely a hardware question. I don't know right now, because there's a lot of different technologies being developed that have kind of different capabilities, so I'm not sure where we're
Maybe
at.
like the IBM one, do you know?
So it's called, like the term that they use, it's called state preparation. And it talks about this resolution exactly, like how accurately can you make the arrow point 35 degrees here, 17.5 degrees there, you know, exactly where you want it to point, right? So
I mean, that's actually part of what we'll see tomorrow is that when you prepare your state and you're trying to have it be at a certain direction, at least with the classic platform, you give it an error that you're okay with. I'm okay with it pointing in this direction to this accuracy. And the more accurate you want it, the more rotations it'll take to get to that exact honing in on it.
And how do we know it's actually in the rotation that we're expecting? Because we are talking about a quantum state, so.
No, probabilistically. You can measure it if you want at that point, but it would stop the program.
Yeah, exactly, okay.
Why do we have only these operations enabled? Like y, x, y, z, and y, h? Like, why is this?
you have a lot.
Yes.
You have, if you go on like IBM, the Qiski textbook, you will see a lot of gates that you can do. But when we said like H gate or X gate or this kind of stuff, they kind of saved us the trouble. They work with the set of gates that works best for them, and they have a mapping. So if you tell me X, I know that behind the scene, without letting you know, I'm actually doing something different that gives the same answer, that gives the same outcome eventually. So you have all those functions that you can use, and behind the scene, they do what they can do, right? That is equivalent of doing what you were asking them to do.
Yeah.
All right.
We're actually benefiting from the quantum computation part of it, because now the way we're looking at it is looking like in our view and something that we can explain, and we're using logic gates that are deterministic. So how exactly are we benefiting? Besides the fact that we can have many different states, besides 0 and 1, which we can simulate using like a classical computer. When we're using this, how are we benefiting from having it in a quantum state? Of actually doing like a quantum calculation, not something that we're controlling and rotating.
Good question, right? We measure within a certain basis viewpoint, essentially, and we tend to measure in that z-axis. We started off with 0, or which? Yeah. 0. We start off initiating all our states in 0, and we measure in that same axis. And so if you do a Hadamard gate and you end up in the x-axis as opposed to the z, when you measure in the z, it's a 50% probability to be in one or the other. We are telling it to point in one direction, but it is probabilistic in the angle we're looking at.
I'll give you an example. Like the first experiment that kind of showed this, or the way they discovered that atoms or electrons, they have spin, it was called the Stern-Gerlach experiment. You can think about the same way. You have a magnetic field, right, going in the z direction, pointing up, right? Now you have a qubit. If I'm pointing up along the same field, and I will measure the energy for the system, I'll get one value. If I'm pointing against the magnetic field, you will measure a different amount of energy. So this difference in energy tells you if you are at 0 or 1. Now, let's say you put the system in the x-axis, right? So you're exactly in the middle, 50-50 between 0 and 1, right? if you will do this measurement, you will see that 50% of the times you get the zero energy, and if you measure the rest of the times, you will measure the one energy. And this is the superposition that you have. Right, so you have 50% this one, 50% this one. The more you will see, like in the examples that you will get to, you see that you get this distribution of where you are at any given step.
Yeah, I think the question is more that how are we designing the algorithm differently so we can actually benefit from the probabilistic values of the quantum computer.
I guess I don't understand differently on that one. What do you mean by programming differently?
I mean, if we, the way I think about software development today is, you write the logic you want the computer to do, and it does it. But here we have like different possibilities that we don't have from like the classical computation. So the question is, how do we develop algorithms that are actually benefiting from the fact that there can be many states? Because if we just, look at this and you try to use like classical algorithms to, do matrix multiplications, we're just going to waste cycles. We're not actually going to benefit from the quantum properties. So the question is, how do we benefit from the quantum properties besides, how are we designing like the algorithms to benefit from the quantum?
Good question.
Designing a quantum algorithm is hard.
Yes. Okay.
It's hard.
That's why people get their names named after them.
But
Shores, Grovers. But yeah.
let's look like this is the IBM Qiskit notebook. It's like the documentation hub. You can read about a lot of stuff there. The show algorithm basically is a hack because we're talking about like factoring prime numbers, but it's actually it finds periods of a function. It just happened that it solves the problem. Again, like it's luck. So here you see an example of a period of a function, okay? And then this is how you implement it. Use those U operators. But more specifically, this is the algorithm you're executing. So this is the circuit. First you apply Hadamard gates to your first n qubits. Then you need to do these U operators one after the other. So what is this U operator? It's like a black box, you have everything inside. And at the end, you need to do the adjoint of a quantum Fourier transform, which is another thing that you can do on a quantum computer. It's the same idea of a Fourier transform, but using a quantum computer.
Oh, nice.
If you do all of this, the answer that you'll get in the end are those two numbers that you need to crack the encryption. Why? So this is
Yeah, so basically
and you can see like
control a quantum computer, but we're not actually going to directly benefit from it being a quantum computer, right?
no, like
You absolutely are.
Because if we're not using algorithms such as this one, which is named after a person who researched it for a long time, we're basically taking like the classical computation thinking and applying it just to a new computer that we're not, per se, benefit.
Oh, no. Every one of these algorithms is thought from the bottom up, entirely different than their classical. We talk about it in classical terms, but if you were to program something, they don't behave like bits, right? A bit isn't 50% probability 0, 1. And you have to figure out, how do I leverage this to do calculations? And so we are using the principles of quantum mechanics and the probabilistic nature of it to do some really cool and interesting things.
Okay.
Yeah.
right. After you got yourself to the plus state, now let's see if you can make it to the minus state.
the IBM stuff and I totally lost him. So we're trying to.
Is it minus when you reach on that side?
Okay, so we do this.
What are minus 8?
So we have this is the axis, so we say this is 0, and this is 1.
Well, this is like rotation.
We have x-axis coming out of the board, so this is the plus, this is minus, and third color.
Yeah. And so what?
Left and right, we have, this is the y-axis, so this is, call it I, and minus I.
Yeah.
Yeah. So is it minus means
This is the starting.
z being
No,
minus?
yeah, just
Oh,
Right?
it refers to which qubit it is.
yeah.
Okay, starting from the index
If
0.
we had one, then it would
Yeah,
be
yeah, yeah.
qubit 1.
Okay.
So we only have one qubit, so it's 0.
Yeah.
You see, we have hints there, supposed to help you, again, because it's not intuitive to think about this rotation, right? Sometimes you can do it in one step, sometimes you need to take several small steps to get to where you want to be at.
The other day.
What is it? Bachelor? I thought it was like bachelor. I'm studying math and physics as well.
Yes. This one is good.
And I want to transfer to American University, but not that.
So now I try to rotate around X, rotate X, so eventually it's rotation on
So,
Z axis.
the way we get to the minus 1, right? We thought about it, if we start at 0 and we apply the Hadamard gate, we get to plus. Maybe if we go to 1 and then do Hadamard gate, maybe it will get us to the minus, right? Because we saw they are connected. And you can also go above and you see if you apply the Hadamard gate on 1, the result is what we call minus, right? So here you need to take 2 steps to get to where you want. So first, we will use an X gate on our qubit 0, right? So if I just run this part,
Something stupid.
it gets me from 0 to 1. Now, if afterwards I add
5 is 2.
an H gate, right? So now my system will start at 0. The first line will make it rotate from 0 to 1. And then the second line will make it rotate from 1 to minus, right? So now that we do both of them together,
But it's not.
we get here.
It depends on what class.
And if this is not complicated enough, and you want to like visually see what is going on, right? We said that X gate is like you rotate around this axis, right? Z gates is like rotation around this axis. Y rotate us around this axis. And this is the H direction. So you're doing this.
And because of
Could you?
yeah.
And this is
I just have a question. Minus one, minus one is plus one.
yeah.
Is there a solution?
So you did X and then Hadamard. If you want to do this, you would need to do
I'll just
Of
you did X and Hadamard. So
Maybe we have like 5 others.
the resolution of the
we're just calling the forward positive in this case.
related with the
It's just a
it is related with the
We're just calling it.
probability to get those in a more cat way
So
and add less
so
noise.
this is the x-axis, but we call it
More related with
plus minus. In the same way, if you scroll down, we don't call this.
It,
Sorry, to the image.
think about it. If
Here, this is the z-axis.
you have
This is the x-axis. We just do it with the labels.
Because here, we're rotating in, I know that this is abstract because the hardware actually is doing a lot of things in the back end to get that rotation.
yes.
That
This is how we're defining this.
and then I start
Really? But I thought it's really.
the resolution of getting, I don't know, instead of 5 degrees, 1 degree.
Minus. Then this is
What will improve that?
plus or minus.
It means that if your system is in 70%, 30%,
Yeah, you know,
And-
you actually drew a
let's make
beautiful diagram on that.
75 and 25%. And let's say your resolution is 10%, like the angle that you can move is like equivalent to 10%.
And
Oh.
that's a whole
It means that you won't get 75, 25%, right? Because sometimes you're supposed to be 0, but you accidentally measured 1 because of the resolution, right? So it will help you make it will eliminate the noise that you get and make the real solutions more visible.
Where
Yeah, it will, like the signal to noise ratio will be better.
And the fun thing to add to this is if you've taken trigonometry or you've done mathematical angles, there's another solution to this, because I did it the other way and then I saw the way you did it. I did Hadamard followed by a Y rotation, and that gets you to the same place. So the order of operations matters.
Yeah, so
was it?
one thing I do want to show you, right? We said that if we want to get from 0 to minus, we need to do X and then H. Does it matter if we do it in this order or in a different order, right? So what will happen if we'll do H and then we do X, right? It's same operation, same things, right? If I add hot water and a tea bag, I get a tea, right? It doesn't matter if I first put the water or first I put the tea bag inside, right? But apparently, this is not all the things in life, and sometimes the order matters. And the mathematical terms that these operators, they don't commute with one another, so you can't just rearrange the order for free. You need to pay some price for it. Or we can say that the group is non-abelian, so again, the order matters. So if you have a recipe, you need to do exactly this recipe. So first you add sugar, then you beat the eggs, then you do that, right? Otherwise you won't get like a whipped cream or something like that. So the order matters. We can do example 4, and I think, yeah. So example 4 is like, again, the same idea. You need to combine gates to get to minus I. And I think because of time, we'll just let it be because it's the same idea. You can't get there in a single shot. You need to combine 2 gates to do it. Right, so I think like the way that I will go about it is let's do, first we move to the X bases, right? So I'm going from here to here, and then I want to rotate there. So I'll use the S gate, which is probably not the right one, probably the opposite way. Yes, so I need S. So basically what we did, we moved, like we said, instead of having a gate that directly move me from Z to Y, maybe it's easier to go to X and then do this kind of rotation. So this was playing around with a single qubit. Now we want to try and do multi-qubit gates. Right? This is the next logical step to do. So we have, again, now that we have more qubits, we have more states. Now everything gets bigger, right? The matrices are bigger, the vectors are bigger. This is why we like the Dirac notation. And you see, like, the math, how it works, how you calculate stuff, why things are the way they are. And again, you see here the syntax that we'll use. So again, same idea. We will call the quantum circuit that we have, and we want to operate some gate on it. But now, because we're talking about multiple multi-qubit gates, we need to specify more than a single qubit, right? So this is an example, the control NOT gate, C NOT gate, what we said, it's like an if statement. So you need to say, okay, what is my control qubit and what is my target qubit? And the control is basically the one I'm asking the question. Should I do it or not? And the control qubit decides basically whether yes or no. And then the target qubit is the one I'm doing stuff on. So I'll ask, should I do the not on this qubit? The answer is yes. I go to this qubit and do an X gate on. Right, so you need to say what is the control qubit and what is your target qubit. And of course you can extend it and have controlled not, right? So now you're asking 2 qubits and you need to consider both of their answers and decide whether you want to operate on the third one. And you can expand it as much as you want, but these are the qubits that we will use. Now, we told you that we can use Bloch spheres to visualize the state of a single qubit. Once we go beyond it and we have more than 3 dimensions, it's hard to do it. So IBM developed this, they call it Q-sphere. And it's a way you can show the states that you have and their amplitudes and their phase. And we didn't discuss phase because it's more like physics related, but it's another property that we have, which again makes quantum computers special about some stuff. But what you need to understand from it is that this example, this visual is equivalent to saying this one. I have equal probability to be at the state 0, 1 and 1, 0. Right? If I'll have different probabilities for each, I will get the same blobs, the same points, but they will be on different places on the sphere. And the higher you are on the sphere, the higher your probability is. The lower you are, the lower the probability is. And let's ignore the color, the phase, and everything. So now you see the answer because I didn't delete it, but we start with 2 qubits now, right? We initialize the system we call a quantum circuit, and now we want it to have 2 qubits in it, so we say 2. So we will start, as we said, because we start always at 0. If I have 2 qubits, both of them will start at 0. So we start at 0, 0. Now we want to get to this creature. Right, and now the question is, how do we do it? And the way we do it is by first doing some manipulation to our system, and then operating with the CNOT gate. So you see the answer because I didn't delete it, but the idea is following. Like, you asked how you think about those algorithms, right? So let's try to think about it together and see if we can understand why the solution is the way it is, right? We start with 0 and 0. We say that at the end, we need to get something where we have 0 and 1, so I do this change. And we want to get this one, where I do this change, right? So I need somehow to change this one and somehow to change just this one. But I need it to happen at the same time, right? I cannot like copy it and just say, okay, on one I'll do X here and the other I'll do X here. Somehow it needs to happen together, right? So the first step, and this is how people think about it, we number the qubits from left to right, so this will be qubit 0 and this will be qubit 1. Okay, so what we say is that qubit 0, let's choose that qubit 0 will be the control and qubit 1 will be the target, right? Now, I want sometimes this qubit to stay, and sometimes I want this qubit to change. And I want them to happen like alternately. So what we do first, we say, okay, let's take qubit 0 and apply a Hadamard gate on it. Okay? So let's see how we develop algorithms. We start with 0, 0. Okay, or like this. So this is qubit 0 and this is qubit 1. Because I want to have this chance of different stuff to happen, I need to make my control qubit kind of somewhere in between, right? The in-between part is doing this Hadamard gate, right? So what happens to my system when I apply the Hadamard gate? So if I apply H, what I will get is that I have ignored the amplitude. This is like 50% off. This will be plus, or like plus, right? It's like 0 and 1. Right, so this is the first part, and we have the 0 which we did nothing to, right? So we have this thing. Why we have this thing? Because we created a superposition, right? Now, qubit 1, the qubit 0, is both 0 and 1. The next step is that I want to actually flip this one first. So if you just try to do it, it won't succeed. You try a different way, and then you see that it works. So you see that you need this X gate, right? So what X gate on this one will do, it will just make it into a 1, right? So what I'm getting is that I have superposition of being 0 and 1. And now the other part is a 1. I turned it from 0 to 1. Okay? The next step is doing the controlled NOT. Now we go and ask, if we write it like clearly, we see that we have 50% of being 0, 1 plus 50% of being 1, 1. So this is almost there. We just need to fix this one, right? So if we use the control knot, we ask it, should I do something to the other qubit? It's 0, the answer is no, don't touch it. So it stays this way. The other one I ask, should I do something to the other qubit? The answer is yes. So if I apply the X gate, this will turn into a 0. So you basically, what you got was this one stays 0, 1 because it says do nothing. Then here we flip this one, so you're getting a 1 and a 0. Not intuitive like we said, but this is how you develop the algorithm. This is how people think, and you do all these trials and errors. So the way you will write this algorithm eventually is that you have H operating on 0, and after that you do X on 1, and then you do a controlled knot. And all of this operates on 0, 0. This is like what if you open some kind of like paper, scientific paper, this is the things that you'll see. So this is how people think about it. Again, not intuitive, not something that you would expect that gives you this answer, but this is it. All right, so
how do you set the probability on that algorithm?
So you start, you have invisible 1 here. Right, you have 100% probability of being in this state because this is how we start. Then we create the superposition on this one, right? So this one has 50% of being 0 and 50% of being 1.
Why 50%?
Because you remember, if we point now at the X direction, you're exactly in the middle between 0 and 1.
So if you change if you change the direction of the spin, you can increase or decrease the probability.
Exactly. This is the resolution we were talking about.
Okay.
The angle, how fine can you rotate your state, right? So if you move to the X direction, now you're exactly 50% chance to be here or 50% chance to be here, if you need to choose, right? If you were pointing like this way, you had more chance to go up than to go down, right?
In what cases I will try to develop an algorithm where I have more probability to have one state instead of other? For example, the same...
You want all your algorithms to have more probability to be at something which is the right answer, right? What is the right answer is a difficult question, but you want your algorithm eventually, after all these manipulations, to have big number in front of the things that you want, or the right answer, right? You want to have larger amplitude on the right answer, because then you will just measure it more frequently, and from that you will infer that this is the right answer.
Oh, I'm trying to digest that.
This is not like a good, like useful thing, but tomorrow we'll talk about something called Grover's algorithm. Grover's algorithm is good for searching like unstructured data sets, or like finding something, like where you ask, let's say you have like a phone book and you want to find someone in this phone book, right? The way you would go about it now is go like, is this the right one? No. Is this the right one? No. Is this the right one? And this is the best way you can do it now, because it's unstructured, you don't have any orders or nothing to it. Grover algorithm has a funny way that you can make this person kind of shine out of the phone book, if you will, right? And you have like a visual description of it, so you can say, this is the right answer, and this is all the wrong ones. And you start at, think of someone, and what the algorithm is doing is it moves your state wherever you start or wherever system, and it kind of like flips back and up, and eventually it gets this arrow to point closer and closer toward the right direction, the right answer. Then when you do a measurement, what you will see that the most probable result that you get is this guy, and it happens that this is the guy you're looking for. Right, so for some you have a visual way to explain the algorithms, for some you don't, it is, but when people are developing those algorithms, they are actually going, now what they have to do is multiply and remember the numbers and add and subtract, and that's what we have now.
A lot of these algorithms, like Grover specifically for me, is one that conceptually still confuses me, but mathematically I get it. If I go through the math of it, I'm like, okay, this makes sense. Putting it into words and that diagram, like, oh, it flips back and forth and somehow it gets to the right answer. That is what it's doing, but it makes sense if you write all the equations like, oh, good. That's what happens. Okay, cool. It slowly gets to the correct answer.
What is the name of that algorithm?
Grover's.
Grover's?
Yeah, like the Sesame Street character Grover. Yeah.
Grover.
Mm-hmm. And that's a very popular algorithm you'll see pop up in other larger algorithms or part of, complex calculations, one that's commonly used.
So let's do like this just to show you the result. So we start with a circuit with 2 qubits. We do nothing on them, right? We don't use any gates. So whatever we get is nothing, right? We have 100% chance of being at 0, 0 because we did nothing. We just started the system. Now we did the first step. We did the Hadamard gate on qubit 0. Let's see what happens now. So here is the circuit that we have. And now what happened to the system? You have 50% chance of being on like 0, 0, like 0, this one will stay, and you have the option of being in superposition with the other one. Now you add the X gate. They can happen simultaneously. They don't need to happen like one after the other. And now it changes to this thing, which is not what we were looking for. But if we had the controlled knot that we had, and telling him that the control qubit is 0 and the target qubit is 1, this is what we have there, and we run it again, we get the answer we want. Now it comes to like a demonstration of this probabilistic nature of things, right? How exactly an answer looks like. So we created a system right here, which technically is supposed to be exactly 50% of the time at 0, 1, and 50% of the time at 1, 0, exactly. So if we'll start in doing all those measurements, we expect to get 50% chance here, 50% chance there, but it's not perfect, and you still have this probabilistic nature. So what we are doing now is we're actually telling it on this quantum circuit that we have, measure it, do a measurement. Here in this case, we run it on a simulator, and we want to count how many times you get each different answer. In this case, we will do 1,000 shots, which means we'll do it 1,000 times, one after the other, and every time we will count what is the answer that we'll get, and we plot this histogram. So now we see we get 490 times we get 0, 1, and 510 times we get 1, 1. But it's not exactly 50-50, right? So maybe we need to run it 10,000 times, right? Now that you run it 10,000 times, now your error is only 0.6%. Now let's run it 100,000 times. Now your error is 0.096%. So the more times, the greater the statistics that you collect, you can be more certain about this probability and the distribution that you get. So in a perfect computer, if you run it infinitely many times, it will eventually land at 50% here, 50% there. Okay, but this is the type of answer that you'll get. Right? If you'll do a measurement, you run an algorithm, you get this distribution, and you need to decide, is it clear enough? Can I get an answer from it, or do I need to run it more to get more statistics and get a better signal? So it's going back, you saw on the slide, right, where we showed all those pillars going, the distribution histogram and stuff like that. Now it's kind of an explanation on a very common algorithm called variational quantum eigensolver. You have an explanation here of what it's supposed to be doing and mathematically how it is doing it. But we don't care about it. We just want to see how we can use it. So a practical example, we want to do a portfolio optimization. Right? You have some spare money, you want to invest in stocks, you want to choose some stocks, right? You can't invest in all of them. So we have an optimization problem with some constraints on it. So basically what you want to get, this is the description of the problem, right? You want to minimize the difference between your variance and your expected return, and you have a constraint that you can only buy certain amount of stocks, right? You cannot invest in all the stocks there. So there is a way that you can convert. We know how to solve this problem classically. We have classical eigensolvers. We know how to optimize a portfolio. It's not a problem. The problem is when you are something like S&P 500, right? Because, or if you hold those ETFs, these indexes that you want to invest in, right? Because what is the problem there? Let's say that S&P 500, they have only 3 stocks, right? So you have stock 1, stock 2, and stock 3. You give me $100. How much should I invest in each one of them, right? Should it be 33% each? Should it be 50, 20, 30? Maybe don't put anything here and just do 50-50, right? So you want to get to an answer. And S&P 500 has 500 stocks, NASDAQ Composite has 1,000 stocks in it. If you want to do it by yourself, you have all the stocks out there in the market, and you need to choose which one to invest in and how much to put in each one of them, and you want to know what is the expected revenue, right? If it's negative, maybe you shouldn't invest at all, right? So as soon as it gets to a much wider and more things you need to pick from your subset, it's getting very complicated for a classical computer to solve it. But there is a tricky way you can convert it to a different problem about spins of electrons. And this one we can solve on a quantum computer, and we know how to translate the answer back those stocks and which one I need to invest in. So again, it's like Shor's algorithm. We are not solving the problem. We know how to solve something different, which by luck is equivalent. So we solve this one, translate the answer. So here we have like all the definitions and stuff, all the things, all the functions that we have. Now, let's look at the problem. In our example, we have 4 assets, and the reason we limited is because we have limited resources we can use on IBM. We cannot use million qubits, right? So basically what it will do, it randomly generates some kind of performance for the stocks, calculates the correlation, the covariance matrix you see here, the sigma, the mu's, everything that you need. And we have our 4 stocks, right? This is the correlation matrix for them. Okay, so we have 4 stocks, and we have a risk tolerance. This is like how risk am I willing to accept? So we set it to 0.5. And out of these 4 stocks, I can only buy 2 of them. I can invest only in 2. What is the right combination? What is the right portfolio mix that I'm after? So because it's a small problem, we can solve it classically. So we'll just use the NumPy eigensolver to get the answer. And the important thing is looking at the results. Right? So on the left side, you can see the selection. How can I choose 2 stocks out of 4? These are all the combinations that we have. You can actually see we have even more than that, but they get 0 probability. The value, think of it as like the return. Not exactly, but let's ignore it. What we care about is which stocks I want to select. So we have stock 1, 2, 3, and 4. If it's 1, it means invest in this stock. If it's 0, don't invest in this stock. Skip it. And you can see that the classical algorithm says 100% probability, invest in stock 1 and 4. 0 probability for the other ones. Okay? This is how a classical computer will solve it. It will get you the exact answer, but it will take a lot of time. So now we want to take advantage of our quantum solutions or quantum algorithm for it. And here basically what you have is you're defining all that you need. You have this variational quantum eigensolver. You give all the inputs, everything that you need. And now let's see, this one will take some time because now it really goes to a quantum computer. So we let it run, and you get the results. So what is the difference here? What do you see that changed from the previous solution?
The probabilities have changed. There's a lot. It gives you more accurate results for like the likelihood of success. And there's still a lot of zeros, but then you have like at least the first 6 that you can sift through and be like, oh, this is the amount of risk I can take.
So again, what you were saying is like we get an answer, but it's not a definite one, right? It has some options that it came up when we did the measurements, but they came in different probabilities. The top one that we see is the same one, same solution, which is good, right? Because if we know that this is the exact solution, we're glad that this is like the top one. And you see that we get it 87% of the time. This is what the algorithm says is the best solution, the best mix. But you also get this option 8.5% of the time. This option, 3.8% of the time. The rest you don't get, right? They're too low. And then it comes to the question, is it accurate enough? Am I sure? Can I trust this result? If I think that 87% chance that this is the right answer is sufficient, then I'm done. If not, what I'll need to do is run more shots. So instead of like 1,001, I can do 10,001. It will take longer, but it will tighten up the probabilities, and I'll see that the probability for the right answer will get higher, and the other ones will get lower. Right? So it's kind of like if these are all the options that we can have, right? And when we use it 10,000 times, we get something like this. We measure it a lot, and we will get more and more and more out of it, and less out of this one. So you will get something like this. So now I can say, okay, now I'm sure that this is the right one. It's not 100% like we got with the classical solver, but I'm pretty sure, like within the risk level that I defined, I'm okay with this solution. Right? So this is like the difference of solving the same problem with a classical solver and a quantum solver. And we just used 4, but again, if you have more and more, it becomes more, it leans more toward the quantum solution.
Why, if we do only one iteration, it gives many probabilities? Why is that? Shouldn't it give only one solution? Like perfect, even if it's wrong, it should give only one solution and not probabilities for many. Or actually, yeah, never mind. It's a stupid question.
No, it's not a stupid question, but if you look, we ran it actually 500 times.
Yeah. No, but if we ran one time, then of course we would have probabilities for multiple.
No, actually, if you run it just once, think about it.
Yeah.
You ran it once, you got an answer, right? 100% chance this is the right answer.
Well, no.
Now you run it a second time, and you get this result. So now it's 50-50. You run it again, you get this one. Now you're 67% sure that this is the right answer. And the more times you get it, you will get some results, but you hope that the right one will get most of them.
But if you try removing 500 and putting 1 instead, and you will see that there are probabilities for every option. On the end, the max iteration.
But it doesn't reach.
Yeah.
An easier way I can show you, like if we go back here, right, to this example,
Okay.
right, when we did all those shots here, if I'll do just a single measurement,
Yeah.
I get 100% chance this one because this is the only thing I know.
It makes sense, but for the last one, if I only put 1, then I have probabilities, like non-zero probabilities for almost every option.
Because the setting you're changing is the maximum iterations. It's not the number of shots you're putting through the system.
Oh, iterations does not equal shots?
Yeah, it's using whatever this command is, Cobila, actually. I'm not familiar with that one.
It's constrained optimization by linear approximation. It's a type of algorithm.
But yeah, it's
Where
not
exactly-
translating to the number of times you're running through the system.
Iterations meant shots. Okay. Yeah.
Maybe reps.
Yeah.
If we do one here. Yes, I think the reps, this is the value that you want to change. Right now, we kind of did, again, the reason, if I show you, On this slide, we said that when you solve the Schrödinger's equation, first you get all the possible outcomes. This is the first thing you calculate, and then only after that you can calculate the amplitude, the probability for each one of them. Maybe the way that the algorithm works is that it calculates all those combinations, all the possible outcomes, and it just gets all of them, and the more times you do it, it just updates those values, but you still can get the values for them, right? Because you're solving for this, right? You want to get those lambdas, those e's, for example, and those states.
Okay.
All right, so that's the example that we had today. Any question before we talk about the plan for tomorrow?
I'll definitely say, right, if any of you are confused at any point of this process, it's for good reason, right? This is not easy, right? This is typically when companies hire on somebody to program quantum computers or start their quantum initiatives, they're hiring PhD level, quantum computing software developers. That takes that kind of knowledge to know this by heart. How do you get this probability? Okay, well, I do X and Hadamard and then boom, boom, boom. And how do you make an algorithm out of that? Well, you put this together, you put that together, and well, if you want to run on this hardware versus that hardware, oh, I can't use that gate. I have to use this gate because that's not native to that. There's so much minutia that comes into programming these systems. And right, we're doing 2-qubit systems, right? The ones we're doing by hand, right? Like I said earlier, IBM just came out with their 1,000-qubit system. Imagine doing this step by step by step by steps, calling out each Hadamard, X gate, things like this, right? It's programming at this level is tedious, but also requires a huge amount of foundational knowledge and having to understand all of this to a degree that you can just natively program it. So, right, fear not if you're confused about this, right? Tomorrow, and the one I'm excited about is kind of the business case for quantum. Today was the academics, right? Learning what quantum computing is, learning this fundamentally, knowing that this does boil down to linear algebra and its rotations and probabilities. And tomorrow we're going to use this. We're not going to go at this gate level anymore. We'll show the gate level so you can see what it looks like if you wanted to peer into it and see, okay, if it's this many gates and this orientation. But tomorrow when we get to the workshop on programming it, it's more about looking at the amount of resources it's going to take. You can have your algorithm you want to run, you tell the system, I want to run this, it'll give you your circuit, and you see, okay, this uses so many gates. It's going to take this many steps to compute this. And so you can start manipulating your algorithms at that higher level. Instead of putting it in by hand, you can start doing, resource allocation considerations. Yeah. Do I want, a problem that has more time steps and fewer qubits because I have a small computer I'm going to run on? Or do I want, maybe my computer has a bunch of qubits, and so I want to utilize that and minimize the error that might occur in my system because, right, qubits are noisy, and the longer they'll go, the more error they're prone to, so shorten that up. And so you can get into these kinds of class of considerations instead of, how do I rotate this to do the calculation I'm looking for? Because even, right, we showed the 2 rotations. There's 2 ways to get to that same rotation depending on which step you took. There's multiple algorithms that'll do the same functional output. There's more than one way to do, addition. There's something called a quantum Fourier transform addition, and there's something called a ripple carry adder. And sometimes it's good to use one versus the other. And so, right, you can start going into higher levels of consideration as opposed to just how do I rotate this to do the thing I want to. So that's the bit I'm excited to show tomorrow.
Basically, you suffered today. Right? You went through the hard stuff just to get it into your system, just to see and even think about why we need this kind of stuff. Tomorrow will be more, like Eric mentioned, about the applications. Okay, so who cares about it? Who puts money into it? What do you think we can use it? Where do you think we can use it? We can give some examples for it. We'll show you algorithms. And then tomorrow, when we will use Classics platform, you will see that basically what the business case for this company is to say, we don't want you to do this part. We don't need you to be a PhD student in order to do it. We'll write the program. You will just do as you come, and you have R or Python or stuff, and you just tell it, do this function. And you don't really care how they code it behind the scene and what is going on there. It will happen. And then you will see that, okay, it's not that bad. Okay, I need to practice, but I get it. I can use it, right? And this is, when we spoke about the challenges, it's getting people to use it, getting people to be familiar, like what can we do with it? Like it's so hard to start when you need to go through all of this just to turn 0 to 1, right? We didn't do anything important. So tomorrow will be more like money.
I'm excited about that part, right?
Yeah.
BCG and McKinsey projections on, how much revenue will this industry drive, and in which, verticals will it be most important to it, and what time frame? Yeah.
Yep. And tomorrow will be simpler.
Yeah.
Will be easier.
All right. So hopefully everyone wrote down their names and email addresses in the book and made an asterisk if they didn't have a classic login yet. I'll send you all an email today with the new notebook to download, because our developers moved so quickly that they updated the software yesterday. So I'll send you a new notebook with that'll run smoothly. And actually, I'm going to probably add something ad hoc, because our developers added something pretty cool to the system I was playing with.
Can you add all pip install in that notebook, because I'm running directly from my machine? Because
Yeah, so we're not going to be using any encoded environment. We're just going to be working in Jupyter Lab or Jupyter Notebooks. And so it'll have all the pipsins there, installs, it'll have all the imports that you need, not assuming that you have any of it already installed. Yeah, perfect. Cool.
Thank you, Rose.
Absolutely, all right. I hope you enjoyed. I'm looking forward to some fun conversations tomorrow.